Here, it says that Jake and Chanel have been asked to convert the square root of 72 into a mixed radical. Jake recognized that the largest perfect square, which is a factor, is 36. So he said that if I take 72 and divide by 36, it's going to be the square root of 36, and the other factor is square root of 2. Square root of 36 is going to be 6, root 2. Chanel thought the highest one was 4, so she said 72, and it's going to be 4 times the square root of 18. Square root of 4 is going to be 2 times the square root of 18. And then when she looks at the square root of 18, she knows that 18 can be divided by another perfect square, which is 9. So 2 times the square root of 9 times the square root of 2, or 2 times the square root of 9 is going to be 3, and the square root of 2. 2 times 3 is going to be 6, and the square root of 2. So even though she did it in 2 steps, she gets to the same answer. Same thing here. If I'm converting the following into mixed radicals in simplest form, I'm going to take that 160, and I'm going to say that's going to be the same as 2 and 80, 2 and 40, 2 and 20, 2 and 10, and 2 and 5. I'm looking for pairs of the same numbers. So I got a 2, I got a 2. The ones that don't have pairs are the 2 and 5, which have to stay inside the radical. So I managed to take 1 2 out. I took another 2 out. And inside the radical, I have a 2 and a 5. And I just have to multiply them back together. 2 times 2 is going to be 4. And 2 times 5 is going to be 10. If I already have a number on the outside, it works the same way. I just need to remember that that's going to be something I'm going to be multiplying by as well. So I can take 98 and say that would be 2 and 49, and that would be 7 and 7. And I'm going to do the same process. I have a pair of 7s, and I have a lonely 2. Well, there was already a 3 on the outside, so don't forget about that. I took a 7 out, and then I was left with a 2 on the inside. This is going to give me 21, root 2. If I'm dealing with application, you don't need to know the distance formula. That's not a requirement. So we're just going to deal with the Pythagorean theorem. So if I went from one point to another point, then I need to just count out how far is it to this side, how far is it to this side, or what are the lengths of the legs of the right triangle that this creates. Well, along the bottom here, it goes 9 across. Up this side, it goes up 3, which means that c squared is going to equal 9 squared plus 3 squared. C squared is going to equal 81 plus 9, or c squared is going to equal 90, which means that c would be the square root of 90. Now I just need to simplify the square root of 90. So I'm going to say that if I have 90, it's going to break up into 2 and 45. Can't divide by 2 anymore, so I'm going to go to 3 and 15, and 3 and 5. And I have a pair of 3s, where one of the 3s can make it out, and then a 2 and 5 are left on the inside. So this would be the same as a 3 on the outside, and a 2 times 5 on the inside, or 3 root 10. If I'm going in the opposite direction, then I'm just going to do it based on whatever the index is. If I need 2 of the same number to take it out, then to move it back in, I need to multiply it twice. So 4 root 5 is going to be the same as 4 times 4 times the square root of 5. Or 4 times 4 is going to give me 16 times 5. This would be the same as the square root of 80. I can do that for any of these. I can say that This would be the same as the square root of 2 times 2 times 6, or the square root of 24. Because it's a square root, I can't move the negative inside. The negative has to stay on the outside. But I can take the square root of 5 times 7, or negative square root of 175. Here I would say that this is going to equal the square root of 2 over 3 times 2 over 3 times 18, or if it makes it easier for you, you can say 18 over 1, because when I multiply or divide fractions, I go straight across the numerator, straight across the denominator. So if I take 2 times 18, then that is going to give me the square root of 72. I'll divide by 3 times 1 is going to be 9, and I can simplify that. 72 divided by 9, it's just the square root of 8. Now, if I am ordering from least to greatest, it's just a fancy way if I want to turn these into entire radicals. So I'm going to say for the first one, it would be 3 times 3 times 5, or the square root of 45. This one would be 5 times 5 times 3, or the square root of 75. This one is already in an entire radical. This one would be 6 times 6 times 2, or square root of 72. And this would be 2 times 2 times 6, or the square root of 24. When they're entire radicals, I can instantly see which is the biggest to the smallest. It's just biggest radicand to the smallest radicand. So this would be first, this would be second, this would be third, this would be fourth, and this would be fifth. And all I need to remember to do is when I'm listing them out, use their original form. So it's going to be 5 root 3 is the biggest. Then I go to 6 root 2, 3 root 5, 2 root 6, and finally the square root of 15 is going to be the smallest. If I'm dealing with cube roots, the same process works. It's just now instead of needing 2 of the same number, I need 3 of the same number. So if you want to just find the factors that are perfect cubes, that's fine if you know what they are. 40 can be divided by 8 is the only perfect cube I can divide out of there, which would be the same as the cube root of 8 and the cube root of 5. The cube root of 8 is 2, so it's just going to be 2 and the cube root of 5. I can do the same thing using my prime factorization. 40 is going to split up into 2 and 20, 2 and 10, 2 and 5. The only catch is now I need, based on the index, 3 of the same number for one of them to make it outside. So I have 1, 2 makes it out. I have a 5 that's left on the inside, and don't forget to include that index. If I'm going in the opposite direction, if I need to turn a mixed radical into an entire radical and it's got a number or an index other than 2, I just need to multiply it by however many times the index says. So in this case, if I want to move the 4 back inside, I would need to say 4 times 4 times 4 times 9. This is going to be the same as 64 times 9, or the cube root of 576 times 9. And that's it.